Okay.
All right, we're good. Okay, so let's jump in. I'm not going to talk about the announcements on the left side. It's all stuff you know, but just remind us. On the right side, hopefully what we're going to cover today. So wrapping up on capacitors and starting with an investigation of charges in motion, which is going to actually occupy us for the rest of the semester. Specifically what we mean when we talk about electric current. So, let's address the question of energy storage in capacitors. Remember, that's one of the primary uses of these devices. And so we want to quantify how much energy we can store in one of these gadgets. Fairly simple analysis. We're just going to imagine putting a certain amount of charge on our capacitor plates. It establishes an electric field. It establishes a potential difference. And if you think about it, that electric field, as it gets built up, is opposing us pushing additional charge onto the capacitor plates, just because there's an electric field done. So since we're having to do work opposing that force, it's that work that gets sort of stored in terms of potential energy. So that's the concept that we're going to follow. It won't be more than a few lines of algebra to figure out how we can describe the energy storage. So what I want you to imagine is that I've got a parallel plate capacitor, and it's already partially charged. So it has a charge which I'm going to label Q prime, plus Q prime on one plate, minus Q prime on the other plate. And we're going to first off define then what is the potential difference across the plates. And at this point I'm pretty much dropping the deltas associated with potential differences, but always keep in the back of your mind it is a difference, it's not an absolute. And annoying, but we're going to follow the standard convention here. So that's the potential difference established across the plates. Once I've got a certain charge Q prime on there, I'm going to add a little bit more charge. So I'm going to add a small differential element of charge, dQ. And as I do this, I have to do work. And that work I can simply describe as dQ prime times V prime. Okay? So dQ prime times V prime over C. There it is. Remind you, the signs, as we've learned over the past week, are always apt for confusion. This is the work done by me as an external agent. It's not the work done by the electric field, which would have the opposite sign. So this is me as an external agent. So this is kind of an external agent, and who's doing the work? Well, it's essentially, if I've got a battery hooked up to this thing, that's providing the impetus or the force that's doing the additional work. All right, so this would give us an expression for the work done. Now I'm going to fully charge this thing to a charge Q. And as you would imagine, all I need to do is integrate this to get what the total work done is. And so I'm going from 0 to Q, and I'm going to now integrate this thing. So it is Q prime over C, dQ, and then when I do this, it looks like the following. And so, hopefully you can quickly convince yourself the answer here is Q squared over 2C. All right, so just remind you quickly what I've done. Very straightforward. We've set up a potential when this thing's partially charged with Q prime. We ask the question, if I push a little bit more charge onto it, dQ, how much work do I need to do? The usual definition of that. And then all I need to do is start off from 0, go up to my fully charged capacitor, integrate this expression, plug in the limits, and lo and behold, this is the answer that I get. Okay? So it's telling us that I can now say this is the work done. And of course, this is now the same as the energy that's stored as potential energy. And so I can write this, and just again, note the sign here. This is a positive relation to the work done. This is the work done by an external agent. It's not the work done by the electric force, if you will. I know you have a question, Eli, I'll get back to you in just a moment. This is delta U. I can, of course, set, and it would be natural to set my 0 point when this thing is totally uncharged. So in that sense, I'm pretty much very quickly getting absolute potential energy stored in this thing. You like what? Say that again. Thank you. Okay, so pretty straightforward. So we've got now this expression for the potential energy stored. And as we'll often find, it may be useful in certain situations to play around with our defining relationship that involves capacitance. And again, I'm dropping deltas at this point, but Q now equals CV. This obviously is in terms of Q and C, but since I have this relationship, I can just commute it by substituting as appropriate and get this either in terms not of Q and C, but in terms of Q and V, or in terms of C and V, okay? So there are three equivalent expressions, totally trivial to do that, but the sort of one that we get from doing this simple integration of work done is Q squared over 2C. All right, so that's now given us an expression for the energy stored. Let me just write this in one variant. So I'm going to make use of this, because what I want to do now is move on, not just ask the question and answer the question, what's the total energy stored, but it's also often useful to know what's the energy stored per unit volume between the capacitor plates. Yeah.
Can you explain what happens to dW in that fully charged energy?
What do you mean?
The dW. I don't understand.
Oh, sorry. Yeah. Boy, I gotta wake up. So this then should be the integral of this, and then this is the integral of that. Okay? Gotta wake up. Yes, thank you very much. Okay. So I'm going to make use of this and recast it in terms of C and V squared. So let me take this. So again, one permutation here giving us the total energy. All right, so this is the total energy. What about the energy per unit volume? So energy per volume, or the energy density. I won't ask you much about this in general, but it's just nice to understand that this is sometimes an interesting parameter. What I'm going to do now is write this as the following. So usually you'll see this expressed in simple term as a lowercase u. Obviously that's hard for you to distinguish in my writing on the chalkboard here. This one, as you know, has always been conventionally uppercase. And I hope our textbook follows this convention. So in this case, it's simply defined as the total energy over the volume between the capacitor plates. So for a parallel plate capacitor, just A times D, plate size and separation between the plates. And so this, with this use of the expression for the energy stored, 1/2 CV squared over AD. So there's that. And I'm just going to play around with this a little bit. First off, I'm going to remind you that, as we learned last time, the time before, if I think about it, the capacitance of a parallel plate capacitor in terms of its physical parameters is that. And the other thing I want to remind you of is that E is, okay, I'm going to write it in this way, minus delta V over delta S, so just a change in potential over some path length that I'm traversing. We're assuming that this is a uniform electric field, so we've got constant delta V per delta S. So I'm just writing it as deltas. And this means that I can write that E squared equals V squared over D squared for these particular parameters, okay? So this is just E equals V over D for our particular variable definitions. I'm going to square it. I'm going to take this. I'm going to take this and fold both of them into this just to get this expressed in terms of some other variables. And you'll see what this looks like right now, namely that. Okay, so let me just highlight a couple of things and then we'll briefly summarize and talk about it, and then we're going to move on. So there's that result. There's this result. This one's sub-3 for another permutation. So all I've done here is do my usual substitutions here. I'm substituting for C. I'm writing V over D as E, and if I write this with the appropriate D in here, I can simplify this, and it tells me the energy density is simply related to the square of the electric field. Okay? So our geometrical parameters drop out, and it turns out this works for other geometries as well. So basically this is telling us as we ramp up the electric field, we square the energy density in our capacitor array. That's about it. That's all you need. So in terms of energy, just make sure you understand how we derive it. Most often you're just going to use the resulting expressions primarily. And again, less important for us generally. For those of you who may go on to be electrical engineers, this may turn out to be very important, but otherwise for us, not so interesting. Okay, quick questions on the calculation of energy stored in a capacitor. All right. I've mentioned to you, I think at this point last week, one very dramatic use of capacitor banks storing energy. I'm not going to show you any of this, though there are some kind of fun promotional videos for those of you that are interested. But by far the largest application of capacitors for energy storage I'm aware of is in the setting of this facility called the National Ignition Facility in California. It's a Livermore plant. Its purpose is a research facility, development facility to try and achieve break-even nuclear fusion. Obviously a very important long-term goal. I would say primarily for future sources of energy. This is run by the Department of Energy, so it turns out it also has very important applications for weapons testing, verification. But how this thing works is it is making use of basically ideas of inertial fusion. For those of you who know anything about this, it takes a little pellet of nuclear fuel, which is typically some kind of isotope of hydrogen, puts it in this tiny little vial, and then blasts it from all sides with incredibly powerful laser beams. Okay? The goal is to heat up and compress the fuel, if you will, in that little vial of hydrogen isotopes. Compress and heat it so much that it undergoes nuclear fusion. And so this requires enormously powerful lasers, and it's very impressive to look at these kind of promotional videos about it. These are lasers that are in pulsed mode, so they basically fire for a very small fraction of a second, and again, they're very powerful. So they need to be essentially initially powered by energy stored in capacitor banks. So this facility, when I last checked, every time it does one of these so-called shots, when they fire lasers into this nuclear fuel, the capacitors store about 400 megajoules of energy, which is a very large amount of energy. And in fact, they release it in this tiny fraction of a second, which corresponds to about 100 million amps of current over this tiny fraction of a second. So these are incredibly impressive capacitors. As I mentioned to you last time I said this, the capacitors themselves are huge. They're kind of, 20 feet tall, and there are thousands and thousands of them in this large shed, the Lawrence Livermore National Lab. So if any of you are ever in California and able to visit, it's kind of a fun thing to go and learn about. All right, so let's get back on topic. What I want to do now is turn our attention to capacitors that are modified in some way, and they're modified by the addition of something between the plates of the capacitor. And what we're going to put in here is an insulating material. It becomes known typically as a dielectric, for no particularly obvious reason that I'm aware of. But if we put an insulating material between the plates of a capacitor, we're starting to talk about something called a dielectric. So why would we do this? Well, it turns out we can increase the effective capacitance of one of our capacitors by doing this. And as you're starting to see, maybe that's useful. I mean, I'm kind of drawn to this to begin with. Let's say I've got a certain potential difference I can apply across a capacitor. If I stick some dielectric between its plates, this is going to increase, and so I can store more energy. So a very obvious practical application. There are others, but that may be one of the most obvious. So I want to talk a little bit about what changes when we introduce one of these dielectrics. We're going to start off with a kind of hand-wavy phenomenology. Just give you a little bit of a sense of some of the parameters that change. Then I'm going to look in a slightly more detailed way at what's happening within the dielectric itself, and particularly what's happening at a microscopic level. We'll see what we can learn about the electric field, the potentials, and the charges in this more complex situation. And then we'll work through a couple of problems. So let me start over here. In pretty much any practical capacitor you might ever use will have a dielectric in it. So obviously of great practical relevance. All right, so capacitor with an insulating dielectric. So it's insulating. Keep in mind our capacitor by definition doesn't have any charge transfer across the gap. That's still true when we put some material in there and, with this dielectric. So, okay, so what happens if we put in our dielectric? So again, some sort of empirical observations. So first off, the capacitance increases, and empirically, we're simply going to describe this by a parameter, kappa. So this is now our, let's say, no dielectric, simple capacitor, so it's either vacuum or air. So this is our default capacitance, C0. Okay? As I mentioned already, the capacitance increases, and it increases by an empirical factor kappa, which is called the dielectric constant for that particular insulating material. I'm not going to write up this table in my notes, but let me just give you a couple of example numbers of what these kappa quantities look like. I mentioned air serves effectively as vacuum. The reasons why you might have a good idea about by the end of today's class, but of course, by definition, vacuum has a kappa of 1.0. If I put air in there, it changes by about 5. Let's see, is this right? Yeah, I think it's about right. 5 parts in 1,000. So it's not exactly the same, but it's close enough to be equivalent to vacuum. So air, in fact, has a value that's something around 1.005, which has 5 parts in 10,000, I guess. Okay, air is effectively vacuum for our purposes. If I take some actual interesting materials, like a chunk of paper, and stick this between my capacitor plates, I have a kappa value that's maybe 3 or 4, not so much, but also not negligible. You will find with certain materials, this isn't a particularly common one, I don't think, but if you take pure silicon, for example, it has a kappa value of maybe 10 or 15. And actually pure water actually has a pretty large kappa value, something like 80 to 100. And you may think, well, water's not an insulator, but of course keep in mind the important distinction between water that comes out of a faucet versus, let's say, purified water, which has ionic elements in it removed, okay? So impure water is indeed a good conductor of electricity, but if you take out all of those impurities, it actually becomes a rather good insulator. So with very pure water, you could imagine having water between the plates of your capacitor and introducing its capacitance with maybe values up to about 100, something like this. All right, so here's the first empirical relationship. one thing to think about that is if I have, again, I've got a certain potential difference that I can apply across my capacitor plates from some external battery. If you think about this, it implies that for a given V, maybe coming from outside, I can have more charge on my plates as well. Okay, so there are a number of sort of just obvious consequences of this. We'll talk about a couple more of them in just a moment. All right, let's see, what else? Let me just say a couple of things about what this might look like. So let's say I have a capacitor with a fixed charge on its plates. It's initially in vacuum, but then I add a dielectric. So what does that tell you? Again, if I've got a fixed charge on the plates and I add a dielectric, what do you think is going to happen to the potential difference across the plates? So I've got a fixed charge and I put a dielectric. What happens to V when I add the dielectric? So again, I just want you to get me thinking a little bit about some of the sort of qualitative behaviors.
Yeah, decreases.
Yeah. So I'm going to get a decrease
Yeah.
in potential why.
I guess qualitatively it can't very well, but I'm just thinking of the capacitance relationship Q is equal to.
Sure, that's good enough, right? So it's basically just playing around with this. I'm going to require that I fix this somehow. Now I'm going to throw in a dielectric. This increases, this has to decrease. Okay? So these are all things that are not difficult, but I find when working problems with dielectrics, which we're about to do, it's easy to get a little bit confused about what these sort of basic underlying phenomena should be as you go through some of the calculations. So that's certainly true. We would expect the potential to drop. And if this drops, so answer here, so V decreases, what do you expect to happen to the electric field? And this is going to lead us on to looking at this at a microscopic perspective. What do you expect is happening to the electric field between the plates if the potential difference is dropping? Good man. Yes. Okay. So remember, we've got our simple relationship between E and V. All right. So these are all things that we should expect. It turns out empirically that I can write this, and it's probably no big surprise, I can write the change in the electric field as just the initial electric field without the dielectric, and it gets divided by this dielectric constant. So that's a little bit of the phenomenology. Let's see if we can take a look at this at a more microscopic level and see what's going on. So, first off, yeah.
So, like, would you think of it like you have a capacitor and you're like shoving a material in between the plates, so that's kind of like reducing the like field in a way, or okay?
Yeah. I mean, there's a demonstration we have. Our technicians out today, so I couldn't show you, but there's a demonstration that does exactly that. We charge up a pretty large parallel plate capacitor, look at what the potential difference is, and then traditionally, you've probably never even heard of these things. There used to be things called paper telephone directories. Yeah, you've never heard of them. Well, they used to be big, thick chunks of paper. If you stick them between the plates of a capacitor, it's obviously a dielectric. It has a dielectric constant of 3 or 4. As I mentioned, the potential difference across the plates drops by a factor of 3 or 4. Okay, so let's look at this microscopically. First off, in terms of the constituents of our material, it's going to be of interest to at least be aware of a distinction, though in practice the end result is the same. And what distinction am I talking about? I'm talking about the distinction between so-called polar and non-polar insulators, dielectrics in our new jargon. you know enough now to be able to hazard a guess what this is, maybe even more than hazard a guess, you probably know. So what's the distinction between, at the microscopic level, constituents that are described as polar versus non-polar? And just to get your brain thinking along the right track, remember some weeks back we talked about electric dipoles, dipoles. So let me get some new volunteers. Polar versus non-polar molecules. Go ahead.
If we're talking about the dielectric, it's polar.
Yeah, the molecules in the dielectric.
It's all facing just one side of the capacitor.
Okay, so let me just repeat what you said, that they're all kind of facing one direction towards the plates of the capacitor. Okay, so let me push him a bit further. The difference between polar versus non-polar molecules in this context. What's a polar molecule?
Doesn't it have isn't it like more negative than like one in one atom than like the other atom? So it's like a
So there's an
a
intrinsic,
dipole?
there's a built-in electric dipole in a polar molecule. Exactly. Water turns out to be a very good example of an intrinsically polar molecule. I don't know any chemistry, but I know that a water molecule is asymmetrical. And that's part of the reason why water has such very unusual properties. You don't think it does because you use it all the time, but water is very unusual. So it has an intrinsic electric dipole moment just by its atomic construction, so to speak. So this is something that has an intrinsic electric dipole. That's a polar molecule. Obviously a non-polar molecule does not have that, so in some sense it has symmetry, at least in terms of electric fields internally. So what might happen if I stick material that is either polar or non-polar into an external electric field, namely in the plates of a capacitor that's charged? So what's going to happen? Come back to your response, which was the right one. So say it for us again. What's going to happen now?
It's going to face one of the sides of the capacitor, so it'll align to the electric field.
Right. So in the case of it's polar, and assuming there's some ability for the molecules to orient with some freedom, that's not always true, of course, and the extent to which they can may be dependent on environmental properties, might depend on temperature, which I'll briefly mention later on. But if this thing can rotate, it's going to tend to, okay? And it's going to tend to rotate in such a way that its negative, or preferentially negative side is facing the positively charged capacitor plate and vice versa. Okay, what about a non-polar molecule? This has a little bit to do with a phenomenon we talked about 3 weeks ago when we first showed the effect of charged objects close to fully insulating materials. Jessica?
Is there like an induced dipole?
There's an induced dipole. So even in molecules that are not intrinsically polar, if I put them in an external electric field within a particular molecule, or even atom, if you were looking at that level, we can expect that there's some preferential shift in the charge distributions. And the end result is kind of the same, right? So in either case, we expect negative charge in each molecule to preferentially orient towards the positive capacitor plate and vice versa. So that's what happens. So either way, we see some level of orientation. And think about this now, and we're going to do this on the chalkboard in just a moment. What's the likely effect going to be in terms of the electric field in the region between the capacitor plates? Now it's stuffed full of this dielectric. So we had some initial electric field, maybe from left to right. I stick a dielectric in there, which, whether it's polar or non-polar, has its molecules orient so that within, on an molecular scale, the charges are aligned oppositely. And of course, this is true throughout the material. So what's the likely effect in terms of electric field overall? Yeah. So the positive positive charges in the molecules want to align with the negative charge on the capacitive plates, right? We have unlike sign charges attracting, yeah. There'll be a superposition, for sure. And what can you tell me about the electric field that's established by these molecules that are now oriented compared to the original electric field? It's the opposite direction, right? Good. So think about that. We've got some level of electric field established within the dielectric. It's of the opposite direction to the original electric field. I have to look at the net electric field, which is the superposition